Hello, I'm Scott Dusterhoff, a geomorphologist with SFEI-ASC. I'm going to be talking about a decision support tool that we've been developing over the past several years called the Riparian Zone Estimator Tool, or RIPZET for short. I'll be providing a high-level overview of the tool and showing some tool output in watersheds around the state of California. So I start out here by discussing the overall purpose of the tool, why it was we even developed it. Well, the idea is that RIPZET will help users estimate riparian zone width based on desired function and watershed location. Okay, so the idea here is that we're trying to get away from riparian just being about trees next to the channel. So what we have here is an idealized cross-section going from a channel through a floodplain out to the upland. And the idea here is that riparian functions change as you move farther from the channel. Close to the channel, riparian functions are about bank stability, shading, large weighted debris input, and as you move further away from the channel, the functions become more about filtering and habitat. And so we wanted to develop a tool that could capture this change in function as you move farther into the upland. But we also know that riparian functions change as position in the watershed changes as well. So in the headwater reaches, riparian functions are really about large weighted debris loading, coarse sediment input. As you move further down to kind of mid-watershed transport reaches, riparian functions become more about shading, bank stability, filtering, and then as you move further down the watershed into low-gradient alluvial channels, riparian functions transition into things more like floodwater storage and groundwater recharge. Okay, so again, we wanted this tool that we're developing to be able to capture these functions and be able to size riparian widths based on the appropriate function depending on where you are in the watershed. Okay. So we are using the National Academy of Sciences definition of riparian to drive this tool. Okay, and under this definition, riparian areas are those areas of physical hydrologic connections between uplands and channels that serve variable functions. We are developing RIPZET with funding from the state in support of their wetland and riparian area protection policy. The idea here is that ultimately the state is going to get to a definition of riparian, and RIPZET will then help users estimate the functional width according to what is in that policy. So the overall approach for RIPZET is to use an understanding of riparian functioning with appropriate physical parameters to estimate either existing or desired riparian extent. Okay, and that's important to know. What you can do, what a user can do with the tool is enter existing information and get the existing functional extent. Or the user can enter desired conditions, either some historical reference condition or some restored condition that the user is trying to get to, and can see how existing and desired, how different they really are. Some important things to know about the tool. First, it's a GIS-based desktop planning tool that's meant to be run with readily accessible data. It is meant to be appropriate for any watershed location, as I've already mentioned, steep headwater channels all the way down to broad alluvial channels. It has adaptable parameters that can be updated to reflect local conditions. Okay, it has an out-of-the-box parameterization, but the user can feel free to update the values for those parameters based on their knowledge of their site conditions. And then it's important to know that the tool uses 3 distinct modules to estimate functional riparian extent. Okay, and I'm going to talk about those modules in the next few slides, but before I do, it's important to know that the first 2 modules I'm going to be talking about are essentially existing modules, and we've been using them for different purposes around the state of California for a few years now. And the third module that I'll really spend the most time on is the module that we've been spending the most time developing over the past 2 years. So the first existing module within RIPZET is called the hill slope module, and it estimates riparian width based on adjacent hill slope gradient. And this module is really intended for steep headwater channels. And the targeted functions within this module are large weighted debris input and coarse sediment input. And what we see here on the right is a channel location that is suitable for the hill slope module. And so essentially what this module does is it looks at the adjacent hill slope angle and determines if that hill slope angle is above a threshold value that the module has, which the default value is 20 degrees. And so what the module then does is if it does find an adjacent hill slope that's greater than 20 degrees, it gives a functional width that's based on how many degrees that hill slope is above 20. So for instance, if the adjacent hill slope angle is 30 degrees, that's 10 degrees above 20, so 1 meter for every 1 degree over 20, that would be a 10 meter functional width. The next existing module is called the vegetation module, and within this module, riparian functional width is driven by adjacent hill slope gradient as well as vegetation height. And this module can really be run in any watershed location, headwater channels, all the way down to broad alluvial channels. Targeted functions within this module include bank stabilization, channel shading, large woody debris input, and runoff filtration. And on the right side of the screen here, what we have is a schematic showing all the parts of the computation to get a functional width, and the simple equation that we use, essentially functional width is based on adjacent hill slope angle as well as vegetation height. So just two important things to think about with this module. First, the taller the vegetation, the greater the functional width that's given, and then the lower the hill slope gradient, the greater the functional width that's given. And then if we look at some output of the hill slope and vegetation module, first we'll look at some output for the Santa Ynez River watershed in Santa Barbara County. Okay, we'll start out by looking at hill slope module output. So what we see here, the channel network in blue, and then these shaded areas are the output from the hill slope module. So one thing to notice is that in these steep low order channels, you get a steep adjacent hill slope angles, so you get hill slope module output, but then in the lower gradient alluvial channel here in the valley bottom, these adjacent hill slope angles are much lower, so there is no hill slope module output. That 20 degree threshold was not met. And then for that same location, looking at the vegetation module output, okay, you see a little something different. Thinking about those same locations, hill slope module output in the steep low order channel, not so for the vegetation module. The vegetation here is very low or non-existent, therefore the module does not provide output. And then similarly for the lower gradient alluvial reach, no hill slope module output, but the vegetation module indeed gives an output because it does have vegetation there. So the idea is that the user can overlay the vegetation module output on top of the hill slope module and get a functional width estimate for channel reaches throughout a watershed. Okay, these two modules can be run watershed-wide. And then the third module in RIPSET, the module that we've been spending the most time on the past couple years, is called the hydrologic connectivity module. Okay, and so within this module, riparian functional width is based on a flooding extent estimate. And this is really intended for lower gradient alluvial channels. And we've been using North Bay watersheds, watersheds within Napa County, Marin County, and Sonoma County as our laboratory to help us develop and validate this module. Targeted functions include runoff filtration, floodwater storage, and groundwater recharge. So the idea here is that these riparian areas, before we came in and developed them, their functional extent really got out to the extent of these larger floods. So within this module, we use very simple hydraulics to get a very coarse estimate of large flood extent, and then use that to help drive an estimate of functional riparian width within these low gradient alluvial channels. So I'm going to walk through how Hicon works. Okay, there are essentially two steps to the module. In step one, the module uses channel physical data with a very simple hydraulic equation, Manning's equation, to develop a local rating curve or a local relationship between flow discharge and flow stage. And what I show here is Manning's equation. Flow discharge is a function of roughness, flow area, average flow depth, and channel slope. Okay, very simple equation. So the concept being, if you have your channel cross-section and your slope and roughness data, you can get yourself to this relationship between discharge and flow stage. And then in step two, the module uses that information, the cross-section and the rating curve, to determine local flood inundation extents for large floods of interest. Okay, so the concept here again, cross-section information along with your rating curve and with flood frequency information, okay, the peak flood values for large floods of interest. We usually think about the 2-year flood to the 100-year flood. With those two pieces of information, the user can then get flooding extent on their cross-section for the large floods. So far, we've been concerning ourselves with the flooding extent for the 10-year and 50-year floods, because that's what the literature tells us are the important flooding extents in the West. But the user can feel free to use any other flooding extent that he or she sees fit for their site based on better information than what the literature provides. So let's look at some output from the Hicon module. Okay, this is Corte Madera Creek in Marin County. And so I'm going to show you estimated flooding extents for the 2-year, the 10-year, and the 50-year floods. But before I do, I'll just quickly walk you through how Hicon does what it does. First, what Hicon needs to run is a site location, either a shapefile or coordinates. And so in this example, our site is here. So the next thing Hicon does is after it gets its site, it defines the study reach. And so it looks 20 bank full widths upstream and 20 bank full widths downstream to get the upstream and downstream extent. And then at those 3 locations, what the module does is it pulls in LiDAR and it cuts cross sections. Okay, so upstream, middle, site, and downstream cross sections. And then at each cross section, what the user then needs to do is go in and provide roughness values for the floodplain, the channel, and then the adjacent floodplain. Okay, so with all that information, Hicon now has cross-section information and the local rating curve for these 3 cross sections. So then the next thing it needs is the flood frequency information to get the flooding extents. And so within the Hicon module, it uses some regional USGS equations with some local correctors to come up with estimates of the 2-year flood through the 100-year flood. Okay, and so once it does that and the module then runs, it provides flooding extents for the 2-year flood here in green, the 10-year flood here in yellow, and then the 50-year flood here in blue. Okay, these are very simple coarse estimates. This is not complex hydraulics, a very simple equation, but these are very useful estimates to get to a functional riparian extent. And then the user can also look at the Hicon output with, let's say, the vegetation output to see how the functional widths compare. So the next step for RIPSAT is the public release. So we are launching RIPSAT in March of 2015. So users will be able to download the tool and instructions from the project website. And so what will be available is the tool itself, which will be an ARC tool as well as an Excel macro. That Excel macro is needed to run the Hicon module. And then there also will be a user manual. And within the user manual, there will be kind of high-level explanations of how the modules work. There will be some information about where the user can go to actually find the different pieces that he or she needs to run the modules. And then there will be some information about how the user can modify some of the data sources to get better output from the modules. Well, thank you very much for your interest in RIPSAT. Please feel free to email me with any questions, and also please stay tuned to sfei.org with more updates about the tool.